So we will continue. Range resolution capability application I already show you. There is some text description for individual scenarios, so you can check it later. And we go for range ambiguity and resolution. You already know what is range ambiguity when we receiving these pools and we don't know, okay, it is right distance, but our radar tells us, okay, it is this distance. So we know it. Then exists so-called staggering, that we changing sending time of PRI, and from this inequality we can get right answer. I will continue. And how we can do it? There is just base formula that I show you yesterday, and now I have one real example how is processed. So imagine we have PRI 1 millisecond. Real target is in 210 kilometers. So now it is non-staggered PRI, so it is mean it will be constant bad value of distance, of range. So we will continue all these values. I think that we will do it together, but we need to save the time, so I will show you result. If we will continue, you can see that the time delay, true time delay is 1.4 milliseconds. Unambiguous range is about 150 kilometers. So we are outside. So is it clear that second pulse already is transmitted before we receive echoes from first target from first pulse? So, okay, 150. And what we are measured by radar, we measure T true. Of course, we know it in advance, but generally you don't know. Modulation PRI, modulation 1, and results is 0.4, not 1.4 milliseconds, but 0.4. And if you could recompute, so measurement range is 60 kilometers. You remember it was yesterday example. So if it will be static target with any PRI, you will see 60, 60, 60, 60, 60, 60, and you think that is static target in 60 kilometers, but it is not true. He is in 210. So now we have completely the same target, but PRI we have two. 1 millisecond, it was previous case, but second will be 1.2. So it is mean first 1 millisecond, second 1.2 millisecond, and it is just changing like 1 millisecond, 1.2, 1 millisecond, 1.2, and so on. So first, now we have two unambiguity range. Why? Because from first pulse and second pulse, I think that is clear. So first is 150, it is same, of course, and second is 180. What is measured target range by primary radar system? First, okay, 60 kilometers, it is wrong. Second, it is again modulation, but by second pulse, so it will be another modulation only. 30 kilometers, not modulation, modulo. 30 kilometers. So I have now two results, 60, 30, 60, 30, 60, 30. Both wrong, I know. But how I can from these two bad values correct value? It is by how to find exact right value range. So the true range must satisfy this condition. It is first measure value, but second measure value. So it was 60 and 30, or what? Yeah, 60 and 30. Modulo unambiguous 2. So we can compute from this true range. From this one. But we have problem. What is T? We don't know T. This is no problem, this is no problem, but T we don't know it. But we know that second condition Yeah, this is the second condition, sorry. So stagger computation, and now how we satisfy this one. It is this one is greatest common divisor. You know. So from 150 and 180, the greatest common divisor is 30. So if I will use this equation divided 30, the result will be this, and the result will be this. So real target resolution is measurement plus t. It is the original equation, but t is 1. So 60 plus 1 multiplied 150. Win-win situation, 210. So you can see how staggering helped me resolve this ambiguity range resolution. So you can see it is easy, but I want to put this example because you can easily follow. This is example how looks in real, because I always show you first PRI, first pulse reflection, first pulse reflection, first pulse reflection, and you can see that this is 210, but radar tells me 60. But in reality, you don't see this one by one, but you always see this one only one time. So I will send and second send and receive, but from first one. It is from second one, and so on and so on. It is always mixed. Understand me? So it is ambiguity. There is script that show you just this picture, but again it is variable, so you can change this position, target, position, answer, response, and so on and so on. So you can play it with this parameter. But now I think that is not necessary because it is just about visualization. Second is staggered. So 1 millisecond, 1.2 millisecond, 1 millisecond, 1.2, 1 millisecond. You can't recognize, of course, because it is very similar value. And you will receive this one. Check. First, answer. Second, but second another answer. And now you can see that this size and this size always is different. There was constant. So it is these two our values. And from this I can solve the equation that I already show you. So it is this one. There you have name of script, so you can try it, play with it if you want. And there is example how works in real. I make just some GIF, yeah. Because this is produced by this script, but due to that, if you want to run it, you can easily without any problem, but it is very slow because it is due to generation of this GIF. So I don't want to run it because it takes 1 minute or something like this, because it is very slow. But you can see what you see like on radar range 60 kilometers, still constant, but bad. There you see 60, 30, 60, 30, 60, 30. It is due to different PRIs, 1 and 1.2 milliseconds. It is also bad, but we can solve. Oh, thank you very much. Okay, can I continue? Again, you could just run it. You have scripts, so just use it. And there is a last script, for example, staggered or non-staggered. It made all calculation of this equation automatically. So you can just run it script, change value, and you will see results. So you don't need to compute manually and solve this solution. And always is presented just this picture. So on this screen you will see non-staggered version. There you will see staggered version. And there is a reconstruction of numbers. So you can see one value, second value, one value, second value, and so on. And where meet each other together, it is our solution of our equation. It is 210 kilometers, you can see this one. So easily just change target distance, I don't know, to 250. You can change position of staggered PRI like 1 millisecond, 1.3, 1.4, and everything will be recomputed. So you will see true delay, it is exactly right value. You will see what is module measurement delays and correspond distance, and how is solving solution and what is result. So it is like this. It is 3 scripts, 2 for visualization, 1 for computation, and you could put almost any values. Of course, you need to be careful and not put if this is 1 millisecond, this 1.1, so you can't put that this will be 1 second or something like this. You need to put some reasonable values, because I don't put to this script some boundary condition or something like this. So be careful, but for normal real values working fine. There we will talk about radial velocity measurement. You already know that is very, very similar to ambiguity measurement of range. Again, we need to solve this blind speed. Blind speeds mean that target with blind speed, this one, where k is integer number, 1, 2, 3, 4, 5, it is multiplication, k multiplied by c divided 2, it is constant because it is speed of light, PRF, pulse repetition frequency, and carrier frequency. So why I care about blind speed? Because radial component is varies from Doppler frequency. Doppler frequency is min fc to r divided c. So we evaluate the subsequent received pulses phase. Phase is derivation of frequency, and from frequency we could derivate, of course, speed. So why, and last thing, why there is n? Because I can have it multiple pulses in one CPI, coherent processing interval. It is just about this one. So this is signal model. It is example of signal model. So imagine that you receive from Doppler phase across pulses. You unwrap phase over CPI or use FFT. There is 2 approaches. So imagine you will get one sample, second sample, and you will evaluate what is difference between phases, between 2 samples. Then between second sample, third sample, fourth sample, 5 sample, and continue and continue and continue. And what is unambiguous Doppler or blind speed, because it is the same almost. It is mean sampling at PRF. Do you No. Do you remember slide with fast and slow time? It is this one. So, maximal Doppler depends on pulse repetition frequency divided 2. And Doppler must be lower than this value. If will be higher, we have ambiguity speed. So, if I will recompute, I can maximal speed will be lambda multiplied with p ref divided 4, and blind speed will be m, this one, where m is integer because I always receive same value. It is just multiplication of. So if f there is equal to m multiplied by p ref, df is 0, and we can indestructible. Do you remember that from last lecture, this picture about wavelengths, that we have motion, but phase always due to sample was 0, so we see constant. It was static target. So it is this case. So what is Doppler resolution over a CPI? It depends how many pulses in a CPI. 1000. So it is this matrix. I have 1000 samples, and in each corresponds sample in CPI I compute spectrum. It is second approach. It could be computed from derivation of phase or from spectrum. If will be from derivation of phase, you expect when you use unwrapping of phase that will be linear. And if not will be linear, then is something wrong and there is some blind speed or something like you are outside of control. Or you can do it from FFT. And if you do it from spectrum, what we are looking for? Maximum amplitude in spectrum. And it will be your Doppler shift, and Doppler shift is speed, it is almost the same. So there is two approaches. My scripts again use it both approaches, so you will see computation from phase or from FFT. They produce little different results because it is different approaches, so we will see. So if I have signal model across pulses, I will get this. It is my signal, amplitude, exponential j phi 0, it is some initial phase, plus 2p fd, it is this Doppler shift, and tk is sampling rate, it is in some specific time, plus noise, white noise. So phase increase linearly with time. So we get this one. Phase difference sequence will be always wrapped to minus p to p. Why? What is complex exponential? Unit circle, if you remember. Because Euler equation, it is complex exponential is cosinus omega t plus j sinus omega t. It is unit circle. So we working, of course, always with this one. So if we are computing FFT, it is clear how we look spectrum of discrete signals. It is spectrum that is repeated, always repetition, because it is periodic spectrum. Why is spectrum periodic? Due to complex exponential. You are always in same circle. And what is this repetition of circle? It is this periodicity. It is still same. But I suppose that a lot of teachers already told you this one. So, now there is example. And again, we will see application. We have carrier frequency, pulse repetition frequency, PRI is 125 microseconds, PRF is 8 kilohertz. We have n pulses. So what this mean? It is length of CPI, because I have PRI, 64 pulses, and from this I will get length of CPI. So what this mean? It is resolution of my spectrum, 64 values in spectra. Why? Because I have 64 pulses. If I will have 128, I will have 128 pulses, and so on and so on. So what is unambiguous range? It is about 19 kilometers. What is unambiguous velocity for this one values? About 60 meters per second. So any speed that will be higher than 60 meters per second will be wrapped to base range. So will show me bed speed. It is same like ambiguity range, ambiguity speed, but we don't say ambiguity speed, but we call it blind speed. It is similar. So Doppler resolution will be about 2 meters per second, because it is depends on length of CPI, of course. So please run it. I will just close it. Range. Okay, I will close it this one. So now I will show you first single PRF and dual, so it is mean in burst. So carrier frequency 10, PRF1 8 kHz, 64 bursts and so on. True speed is 150, initial range it is 10 km, and signal to noise ratio is 20, so noise is very small, how we already discussed it, and it is done. So there you can always see results and check single PRF, it is wavelength 3 centimeters, true wire 150, speed computed by phase is 30 meter per second, and by FFT is 30 per second.
Exactly 30%.
Yeah. It is almost same. It is, of course, it is computation, so there you have some finite arithmetics, and there could be some differences, but it is just MATLAB. But check this one. It is not right. Okay, how to do it now, because I need to check. Just we will put, so maximum speed that will be recognized well is 60 meter per second, but I put 150, so it show me 30 meter per second, much lower speed, so it did not works. So just put there, I don't know, 35, 30, something, what is lower than this 60. So if we will put 45, 45, you can see I am inside the region of an, yes, there 45, and check the slow time phase. It is linear. It is without any problem, anything. Do you see? So maximal recognition speed is 60 meter per second. My speed is 45. Identification of speed 45. Works.
So Vmax depend on which parameter? Like,
No. Now I just want to show you when is good results and bad results produced. It is just default parameters, this one, and I just changing true speed of my target. So if based on these parameters is maximum recognized speed is 60 meter per second, and if I will put 20, like example, it show me 20. If I will put, I don't know, 50, it show me 50. If I will put 59, it show me 59. But you can see we are just on the edge. And if I will put 65, I'm outside. It show me minus 55. So it is mean, what is mean minus? The target travel just not incoming to me, but ongoing. If I will put, I don't know, 149, you can see completely bad definition. So what we can this is just presentation of ambiguity speed. So I will put to like 55, so it will works. Now I will show you influence of PRI. So now we have, it was single per F. Now we have double. So what does mean? 2 PRI. Because how we can solve this ambiguity? 2 PRI, 1 millisecond, 1.21, 1.2. Again, it is very similar. So I will switch to 2 and check. One is 8, second is 7.5. Identified first place is 55. Second, give me a second. Give me a second. Oh, the alias set search. No, this works. Oh, give me a second. Yeah, through. Yeah, this works. 55. I am blind. Sorry. So now works. If I will put 150 and I will be outside of my maximum speed, you can see that first give me wrong value about 30 meters per second. Second gives me about 38 or something like this. Yes, 38 and 30 meters per second. So both are wrong, but solving same equation but for the speed, the aliased is 150. You can see it is work like with range ambiguity, completely same. And there is this is like slow time phase. It is difference between phase changing linearly. There, what is mean this the alias search? It is mean range where should be my good speed. Why? Why I need put this one? Because ambiguity is multiplication by integer. If you understand me, I need to know to range. But imagine we have in range 300 meters per second, so it is, you can put it 500 meters per second, so on, so it is not important. I can change also length of CPI. If I will put higher value, what's happen? Main lobe of first and second is narrow. Why? Because it is longer time and inverse value. It is. So if I will put, I don't know, 200, two ambiguities, look. First, PRI show me that speed is minus 40. Second, that is minus 25. After the aliasing, we get right value 200. So it is work. It is exactly same like for range. Only it is solving ambiguity for speed. And give me a second. I will switch again to. And there I already prepare about 20 of scenario that you can test it. Scenario A's, about 10 of them, it is same carrier frequency, single pair F, mode off, same length of CPI, same SNR, but changing just speed. So if speed will be 0, static target, you will see main lobe in 0. If will be plus 42, due to fact that we have maximal recognition speed 60, it will show you peak on 32. Okay, we don't have any problem, everything works. If I will put minus 35, it is okay. It is just mean a negative sign that target goes away from me and not close to me, it is plus minus, so it is clear. If I will put plus 60, I am in maximum speed. It will works, but problem if you put 61 or something, it is just on the edge. If you put 120, it is 60, imagine, it will works for 60 because we are just on the edge. If I will put 120 speed, it will be completely same. Why? It is multiplication by integer, it is blind speed. If I will put 180, same result. 240, 300, 360 and so on, it will be same. Because this mean it is on edge, this will mean blind speed for m equal 1, 180 blind speed for m equal 2, 240 blind speed for m equal 3, and so on to infinity. If I will put 119, it will be same like if I will put 59. It is the same. And if I will put 150, okay, I am out and it show me some bad speed, I think 30 meters per second or something like this. So it is all these scenarios. Then we have scenarios B. There you will changing PRF. So PRF you will stay same and just change PRF. It will show you that just you can change it 1 or second and solving will be always. So that is not only for some specific exact value you can changing this one. So only what is will first alias will be 30 milliseconds, seconds 37 point, and if you will see this one, it will be same solving but just for another values of PRF1 or PRF2. Then we have C, and it is influence of number of pulses. So if, okay, I will show you this one. It is interesting. So I will switch to 1. So 10, 8, and now we will put 16 and speed back 42. So, do you check this spectrum? We have only 16 number in CPI. So check, if I will draw it in discrete, there will be 16 points. So my velocity recognition, it is not good, it is not nice, because if I will put 32, of course you can, I always make multiplication of 2 because I always use this because due to computation of FFT, it is my habit only, you can put any number that you want. You can see it is more and more detailed. So it is this one, it is C. And signal to noise, no, it is, yeah, signal to noise ratio, we can try it. So is it clear that there is almost not any noise because it is sun rays 20 dB. So let me check if I will 10. You can see noise is higher and higher, but never mind, our phase is still very stable because without any problem. If I will put 0, check, unwrapping of phase. It is still linear relatively, you can see a slope. But there is mistake. Look at this. From phase is okay, my speed is 42. It should be recognizable because it is 1, but now is influenced by noise. And what is influenced by noise? Of course, my signal. So remember, if I will compute speed from like relative changing phase of different sample, it is more and more this sample is influenced by noise, but not only amplitude, phase also. So due to this noise, by this principle we get speed 20 meters per second, but right one is 42. But speed determined by FFT, it is still right one. Why? Because I checking for maximum. And noise increasing, but still okay. So we will put -5. Okay, phase just give up because this is definitely not linear. It is nonsense, and you can see there. Okay, 42. And if I will put -10. Okay, 42, but honestly it is on the edge, -15. Ah, sorry. I have limitation, -10 is the lowest one. But check by the phase principle, it is already gone, it is not worth. This is not linear phase. You can try also put mind speed, and we go to 0, and slope will be, okay, I will put not 0 but 10. So what is mean that is negative or positive value? If it's slope this one or this one, it is the same. And again, you can make any combination what you want for this PRF. Can I continue? Range equation. For this I don't have any script because range equation or power equation is about how many power I need for detection of target of this specific size that is defined by radar cross section and some probability. So output will be 100 kilowatt pulse, 200 something, it will be just number. Sorry, I will just drink. So, just example is, determine the required power, pulse power of precision landing radar transmitter. The radar operates in 3 centimeter band in X band, so it is 10 gigahertz. You can saw it from 3 centimeter wavelength. In clear weather, it should have a range maximum 40 kilometers. Fine. For target of type swirling 2, what is mean? High fluctuation of target. RCS is very fluctuated. Swirling 0 is non-fluctuated, swirling 1 is low fluctuation, swirling 2 is high fluctuation of radar cross section. It is done by table, you can saw it this formula. And this target type is in altitude of 15 kilometers and with an effective reflectivity of 2 square meter. It is RCS. So it is not big. Consider scanning with a side antenna, azimuth scanning, so it is continuous scanning, with the target in the direction of the maximum vertical antenna pattern. What this mean? My antenna, you will be target, and my antenna just looking at you. Because of course I can look at you, but still by side lobe I will show you also. So it is just this projection. And we will neglect effect of multipath. We don't care about multipath. So max 40 kilometer, PRF 3 kilohertz, carrier frequency 9.35 gigahertz, length of pulse, noise temperature, gain of transmitter and receiver is same. What is mean? One antenna, monostatic case. Minimal detection rate is 12 dB for one pulse, probability 0.8, false false alarm rate 10⁻⁶. Classic value that I presented yesterday. It is main lobe width of my antenna, and antenna scan speed is 90% divided 0.6, so you can just it is how quickly rotated. We have target parameters, swirling tip 2, independent on previous pattern, high fluctuation, target this. And my question is only one. Required pulse power for target detection. Which target do you need for detection of this? So, it is required pulse power equation. Required pulse power equation in dB. So, multiplication in dB is plus, division is minus, because honestly it is so big or small values that is hard to work with this one. So, in dB is much easier work. And maximum is at 40 kilometers. So, I take care only about maximum. R is equal to R max. So, it is mean my radar is just on edge of his capabilities, and on this edge I won't see target 2 square meter size of RCS. It is all. So, from the definition of example, target is at the maximum of antenna pattern, so value of this will be 1. We can ignore it, it is 1. Multipath is not considered, so this is influence of antenna pattern, so it is 1. We don't consider that I will get reflection by side lobes. It is 1, only by main lobe. For simplification, I will see only you, not you. What is minimal power? It will be Scenario minimum. It is in definition it is 12 dB. It is depends on what? My receiver. How is quality of receiver? KTSB. K is constant Boltzmann. T is noise temperature, bandwidth, and multiplied by 1 divided GI. What is GI? It is integration of M pulses, because we don't have only one pulses, but we have multiplied pulses in CPI. So M is PRF to M number of pulses. Integration of pulses is equal to PRF multiplied by time illumination. What does this mean? Imagine that this is target and there is radar, and I will send 1 pulse, second, third, 4, 5, and 6 is outside of target. So I will illuminate target maybe by 10 pulses, 100 pulses. It depends on shape. Of course, more pulses, more information, more reflected energy. It is clear. And you can see that this is also depends on speed of rotation. If I will have quick speed, I will get only lower number of pulses. Slow speed, and also on main lobe width of my antenna pattern. It will be big, it will be slim. And now we will evaluate all this value. So just check it. I need compute this one in dB. Okay, so I will put the value and compute some. GI, it is integration gain, because why integration gain? More pulses, more energy. It will be 10 logarithms M in this integration gain. What is minimal power? It will be this. And what is L total? It is in our equation this. It is all kind losses. So we have atmospheric losses, but it is clear sky, so I think that we can ignore them. integration losses, integration after detection versus coherent integration, there is some little difference. Scanning losses during integration due to shape of the antenna pattern. Why? Side lobes. Losses due to target fluctuation, a processing losses. And it's not a lot of, it is not all of them. There is a lot of different type of losses, but rest is we ignore. So, and imagine we start just make computation of this one, just one equation. So this is 1, this is approximately 1, this is this value, number of pulses is 15, so on. There is individual losses computed, total losses is about 4 dB, and my question for this one is receive power must be, or receive power is transmit power plus all these things. So of course I will make evaluation of transmit power from, and transmit power must be higher or equal to 50.5 dB watts. It is approximately 113 kilowatts. And now you know, okay, I need design transmitter that will transmit me minimally 100 in pulse, minimally 113 kilowatts, and then I can detect target with RCS 2 square meter. And I hope that will help you in case that you sometimes need it. You will just put another values and adopt it, and but it is same equation. I don't have script for this because I think that is simple for visualization. Just do it like one by one. But any system engineer start with this. What is requirement? Okay, you want radar short range. Okay, until 50 kilometer. Okay. And on the edge, what will be size of target that you want to detect? 100 RCS, 2 meter square RCS. It is depends on size of target, but it is clear. Okay, we will back to range quanta and Doppler sampling. Still remember? Can I go? Perfect. So we go for example for range quanta and Doppler sampling example. We will have waveform in fast time, what is linear frequency modulated pulse, length of pulse 20 milliseconds, bandwidth 1 megahertz, sampling speed 10 megahertz, carrier frequency 10 gigahertz, range sample spacing will be about 15 meters, pulse compressed range resolution 150 meters, pulse train will be PRF, it is 0.2.5 millisecond, number of pulses 128 pulses, so it is length of CPI will be 32 milliseconds. It is like some typical values. We have two targets, 12 kilometers and 14.1 kilometers with different velocity. One target goes to close to us, second just go away from -9 speed. And both targets are in different. So, what is processing chain? We form the fast-slow matrix. So, we just do it this one. We make fast matched filtering. It is pulse compression. What is it? Cross correlation. And columns become range profiles. Yeah, from cross correlation we know range. So, we know range. Range columns. It is range cell. It will be column, of course, but in slow time across pulses at each range bin. So it is mean there. I will compute Doppler. So it is mean that will be speed. There is some K limits, and now please run this application. Give me a second. It always run in my primary screen. And check 12. Okay, there I have a different how to say, different range. So first target is 12 kilometer, second target is 20.5, and what we can see, yeah, no problem, 2 targets. And why in Doppler spectra I see only one lobe? What do you think? Because both target has the same speed. Yeah, so position is different, but speed is same. Because you can see there is blue and red one, but in male lobe, blue and red one is just same. There I don't have time to finish for changing all these parameters, but I should do it. But please always go to these scenarios, and there is definition of parameters. Yes, okay, it is scenario 1, it is default. Okay, and there is range. So you can see there you can change always the value. So it is mean position of first target, second target. Speed is 0, 0, static, so it is 0 and is same. And you can slowly change. What you are changing there? There you are changing in range only, range, and speed is 0, signal to noise ratio is default 0, and so on and so on. So we will pass now through all these things. This is stagger, I can close it, and we already discussed. Maybe I should update this application and put these values also to control, and it will be better because you can easily change it. But I suppose that you understand MATLAB, so you can change it even in code and not will be any problem. So it is this scenario when we have 2 targets at 0 speed. It is just first example. So second example will be that we will use only velocity. So it will be same range. Okay, give me a second. Same range. We have only low number of pulses, but never mind. But in velocities you can see that they are resolved. I have seen 2 peaks. If it's unresolved, what does mean unresolved? That we don't have enough resolution in speed. And look, there is radial velocity, there is range. It is, you can see there is no resolution of targets. I see only like one target. It will be resolved. Yeah, 2 points. It is like something like this. So you know where is maximum. This is not maximum. Maximum is where is the most red one. I don't know how to say it. Purple one. Joint, it is mean different position, different speed. So you can, okay, I will reset. You can see different position, different position. One is in, we can check it. One is in 14 kilometers. I don't want this. And second is 12. And speed is 12 It is this one. X is sorry. -9 probably, something like this. There you can change it, number of sample, length of CPI and so on, signal to noise ratio. So if I will make signal to noise ratio like 10, or it will be same, -20, but I am not sure if I don't have some limitation. Yes, -20 is still good. -30. Still good. Okay, uncheck, -40. By the way, this is usual. What is this? This is good example. What is this example? Can you see target? Yes, there is still, okay, maybe from your distance it's not so visible, but it is there. But what is the rest? It is clutter, it is noise, it is reflection from environment. And imagine, it is like before MTI, before removing static clutter, something like this. The raw radar data looks like this one. And from this, you need to find target. So, and for this reason, remove MTI, remove clutter by MTI, and then you will see, but it is depends. If will be small reflection, you will not see anything anyway. Of course, this is school example, so in real data are much more complex. And imagine, everything what I am showing you, it is just offline, but your radar must work real time. You can't stop. It will be any second, any update, any rotation and everything. And imagine that this is target and there will be close wind turbine. What's happened? There will be big red something, and definitely you will not see your small target because it is small one. So it is this one. This is some example of reduction by windowing. You probably have some experience with design of filter. You know what is window, rectangular window, and I don't know, Kaiser window, and different type of windows. Maybe not, but never mind. It is just a different type of filter how you want to suppress main lobe and side lobes, some better filters. And this is this one, you could window it. So if PRF will be low, it is a good example. Check if I will make low PRF, pulse repetition frequency, distance is okay, but check why there is nothing. Because my PRF is low, so recognition of in Doppler is, what is there? Blind speed. It will be mapping to this one. If will be PRF high, of course, I am outside, like it is extension of interval. SNR low, SNR high, and it is some preset that I just put for you. Group delay, just ignore. It is velocity aliasing. Okay, there is aliasing of velocity, so it is mean that my target is so high speed that can't recognize. It is ambiguity of velocity again. And if it's range aliasing, it is something similar. It will be again aliasing of range. So it is just some few presets. Everything, please, you have already discussed in scenarios. You have already discussed. And now we will go to last one. Oh, I close it. Pulse compression. Just for example to have it. So rectangular, it is spectrum, since you know it, autocorrelation, but it is in dB for this reason. There, be careful, it is rectangular pulse, it is amplitude, it is blue one, and this is phase. It is red one. So I amplitude and phase characteristic to put together because for me it's better. And again, you can change duration. It will be 2. It will be and there, do you know what is ambiguity function? Okay, it is again show me on my screen. It is ambiguity function of rectangular pulse. Ambiguity function depends on time and Doppler shift. So for each range of time and Doppler shift, you will compute it, and this is cut. So cut for zero Doppler cut. So it is mean zero Doppler shift. It is our triangle, and zero delay cut. It is mean that is Doppler response. It is now our sense function. So this is 3D function, but you watch it this one like from top. This is very useful tool for analysis of quality of different type of pulses, but it's out of scope of this lecture. So you could present it, you could check it, but please check yourself this one. But I just want to show you that this is their information. So, but we go to L05, check rectangular in amplitude, it is constant, but it is L05, linear frequency modulation. So frequency is linearly growing up, instantaneous frequency, and spectrum L05, autocorrelation function, and ambiguity function is displayed in another window and looks like this one, linear. Then L05, you can see this is non-linear, so L05. And Barker, it is phase is hard-coded by Barker code, length 13 bytes, and looks this one. And again, ambiguity function. Looks at this one. So you have different, just different view. But I think, no, I can't do it. I just want to show you in 3D, because where is yellow, it is up, so it is complex shape, but you can present it in 3D also. Okay guys, it is all for tutorial 1. We will just finish all radar things, and now we are back in turbines. So I don't know when is planned lunch, maybe now? 1:30. Yeah, I'll check it. So we have maybe time or not? Oh, 1:30. So we have time. Ah, 12:30. Okay. Okay. I get it. So we will, after lunch, we will work with lecture 3.